In today's note, we are going to look at the vertex form of a quadratic. And specifically, we're going to look at how we can go from a given equation into making a graph. So this is a review, a little bit of a review of what we looked at in the last lesson, where we looked at the transformations of a quadratic. We looked at how the a, h, and k value affected the shape of our base graph or base function y equals x squared. So just as a review, this is our vertex form here. It's the kind of overall form that we looked at in the last lesson, y equals a, x minus h squared plus k. The a value, that controls the direction of the opening as well as the step pattern, that 1a, 3a, 5a that we previously talked about. And we're going to be putting that into use today. The h value, the opposite of this number, or the opposite of what we see in the equation, is the x value of the vertex. So again, if we see a negative, that means our h value is actually positive. If we see a positive, that means our h value is negative. This value is also the axis of symmetry, or basically in the general equation, x equals h. And then k, the last value, that is the y value of the vertex. And this is also known as the optimal or max or min value. And the max or min depends on the direction of the opening. One thing to note, if there is no a value shown, then that means that a is equal to 1. Because a is being multiplied, if I don't see an actual number being multiplied out front, the only number that I don't have to show when I multiply is 1. So if I don't see a value, then I assume it's 1. If I don't see an h or a k value, or there's no h or k shown, which means I'm not seeing anything added or subtracted to x in the bracket, or I'm not seeing anything added or subtracted after the square, then that means that either h equals 0 and or k equals 0. Because when I'm adding or subtracting values, the only value that I can add or subtract that I don't have to show is 0. So just one thing to keep in mind, if we're not seeing values, that doesn't mean these spots shift down or they rotate or they become other values. They have set values if they're not shown. As a review of the transformation, so this is what we looked at in the investigation, looking at Desmos, we found that the a value, when a is greater than 1, we have a vertical stretch. When a was greater than 0, but less than 1, or basically a fraction, we had a vertical compression. And when a is positive, that meant it opened up. Let's say positive opens up, and opposite, negative, opens down. So those are the transformations that the a value tells us. These are the transformations. Again, it still tells us the direction of the opening, positive, negative, as well as the step pattern, which does fall into the vertical stretch or compression. The h value, h told us if h was positive, means it shifts right, and if it's negative, it shifts down, or not down, it shifts left. Remember, h horizontal, so left or right. And again, keep in mind the positive and the negative, that's opposite of what we see. All right, so if we see negative in the equation, that means our h value is positive, which means it shifts right. if in the equation our h, we see positive, that means our h value is negative, so it shifts left. So it's the opposite of what we see. K, we just take it as is, as we see it in the equation. So positive shifts up, and negative shifts down. So what we're going to do is we're going to look at given vertex form equations, and we are going to come up with all these kind of key information or key points, as well as the transformations, and then finally we are going to graph our quadratic so we get an idea of what it looks like. So looking at our equation, y equals x plus 2 squared plus 6, I want to know my a, h, and k value, because then I can use that to fill in my vertex optimal value and so on, and then use this information to graph it. So the a value, again, remember we said if we don't see an a value, which has to be the number that we multiply first, it has to be 1. So if we don't see an a value, it has to be 1. Our h value is the value in the bracket with x, but it's the opposite of what we see. So here we see plus, so our h value is actually negative 2. And then our k value, we just take it as is, which is 6. The vertex, remember the vertex, we're given an h and a k value for our x and our y. So our vertex is our h and k. So in this case, our vertex is negative 2, 6. Just taking the h and k value and putting them in together for a point. Our optimal value, the optimal value was the y value of the vertex. So in this case, it's 6. Axis of symmetry was x equals h, or the x value of the vertex, so negative 2. Direction of the opening depended on the a value. The a value is positive, so the direction of the opening is up. The step pattern, this one may be a little difficult because we didn't cover it too much in the previous lessons, but the step pattern always forms the general, or follows the general pattern 1a, 3a, 5a. And in this case, we basically do 1 times the a value, then 3 times the a value, and then 5 times the a value. So in this case, 1 times a, our a value is 1. 1 times 1 is 1. The next step, 3 times 1 is 3. And then the last step, 5 times 1 is 5. The number of x-intercepts. This one we may want to wait until we graph it, but if we look at our graph and we see that our vertex is at negative 2, 6, so negative 2 up to 6, there's our vertex. We know it opens up, so that means going back, this optimal value is a minimum, because we know regardless of what shape the parabola takes, it's going to go something like that. It's going to open up. So the number of x-intercepts in this case, they're going to be none, because when we graph this, we're going to see that it's never going to cross this x-axis. Transformations we can get from the a, h, and k value. A equals 1, so nothing's happening. That's our normal value. We're not changing anything. H is negative 2, so that means we shift left 2. Our k value was 6, so we shift up 6. And we can see that from our vertex, because if we remember what that general form y equals x squared, that general form of our vertex was right there. And we can see that our vertex of our new one, given from our equation, has been moved to the left 6, or left 2, and then up 6. Now, if we want to graph it, there's 2 ways to do this. There's a way that we base on the transformations, and then there's a way just using the vertex and the step pattern. I'm going to show you first both ways just to show the relation, but I think the easiest way is to always use the vertex and the step pattern. So first I'm going to graph the y equals x squared. So again, you can go back and look or plot it, but in general, this is what your x squared graph will look like. If you want to create a table of values to help figure that out, you can. But basically 0, 0, 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2, 4, negative 3, 9. That's your y equals x squared graph. Now, if I want to plot this graph of y equals x plus 2 squared plus 6, the way I'm going to do that is by applying all my transformations to each one of these points. So the transformations are, it shifts left 2 and up 6. So that means every point on this graph is going to move left 2 and up 6. So I'm going to start at my vertex. I'm going to go left 2, up 6. There's my new vertex. The next 2 points, I'm going to move them left 2, up 6, left 2, up 6. There are my 2 new points. I can't really graph the other ones because they appear off the graph. Or actually, no, I can graph the other ones. Left 2, up 6, left 2, up 6. I can't graph the third one because that one happens to be off, but I can roughly draw it there. So that's my y equals x plus 2 squared plus 6 graph. So that's one way you can do it. You apply the transformations to every single point on the y equals x squared graph, and you get your new graph of whatever the equation happens to be. I'm going to show you the way now of using the vertex form. So all I'm going to do is plot my vertex, which I've already figured out to be negative 2, 6. Negative 2, 6, right there. And the step pattern is going to help me fill out the rest of the points. And the way the step pattern works is, starting at my vertex, I move 1 to the right, and then my first step in the step pattern tells me how far up or down I have to go. So here my step pattern, the first step is 1. It's positive, so that means I'm moving up 1 unit. And at that point, that's where I have another point on my quadratic. The next step, from this new point, I move over to the right 1 and move up the next step. The next step is 3. So I'm going to move up 3, and there's my new point. I can repeat the process on the going in the left direction, over 1, up 1, over 1, up 3. Or I can use the idea of symmetry with my parabola to graph the other side. And there I have my parabola of y equals x plus 2 squared plus 6. So I find this way a lot easier because it's going to give you the same thing. It's less moving of parts, and it's less jumbled on your grid. Both are fine, but again, I suggest using this method because if all we're doing is graphing a new quadratic, we don't really need to see that original one, as long as we understand what the transformations are. So I'm going to go into one other example, and then we'll pause the video. There are 4 examples in the lesson that you can try on your own, and then we'll pop back in. So y equals negative x minus 5 squared. So again, the a value is this first value that I multiply. I see a negative here. I don't see a value. So I know when I don't have a value there, it has to be a 1. The negative tells me it's going to be a negative 1. The h value comes from the value inside the bracket. It's the opposite of what we see. So because I see a negative 5, that means my h value is actually positive 5. The k value is supposed to follow the squared. However, I don't see anything. Because I don't see anything, the only number that I can add or subtract where I don't see it is 0. So this equation is actually -1 times x minus 5 squared plus 0. But because I don't need to show that plus 0 because it doesn't really change anything, I can leave it blank, as long as I recognize that that k value is 0. For my vertex is 5, 0. The optimal value is the y value of the vertex, so 0. The axis of symmetry is x equals h, or in this case x equals 5. The direction of the opening is down because my a value is negative. That means that my optimal value will be a maximum, so I can go back up and add that. The step pattern, again, follows the general form 1a, 3a, 5a. So 1 times -1 is -1. 3 times -1 is -3. 5 times -1 is -5. For the number of x-intercepts, in order to do this, I'm going to plot my vertex to see where it lands. So it lands at 5 and 0, right here. And I know it opens down, so it's going to look something like this. So the number of x-intercepts, or the number of times my quadratic is going to cross the x-intercept or x-axis or touch it, is only going to be once at that vertex. So it's only going to be one x-intercept. The transformations, my a value is negative, so that means it's going to flip, or the transformations, everything's going to be flipped. The h value is +5, so that means to the right 5, or shifts right 5. The k value is 0, so nothing happens with the k value. Now I can plot my graph. I'm going to use the step pattern. I'm going to move 1 to the right. My first step tells me to go down 1, or -1. There's my new point. I'm going to go to the right 1 again. My next step is -3, or down 3. My next step again, move to the right 1, and now it tells me to go down 5, or -5. And there's my next point. I could repeat the same steps on the other side, or use symmetry, because again, I should know or remember that this parabola is symmetrical on that axis of symmetry that goes right through that vertex. So everything on the left side is going to be the exact same as on the right side. So over 1 there, there, and there. Opens down, so connect those dots. So good, we can see it opens down. We can see that it shifted to the right 5, and we can see, then that's the only transformations that we see. So good. So that's our quadratic y equals -x minus 5 squared. Moving on to the next two. So if you have this lesson, I highly recommend that you pause, try to go through these two examples on your own. Work through, again, same thing. If you have to, go back, take a look at the steps that we went through to find the a, h, and k, the vertex, and all the key properties, and when graphing the quadratic. So again, pause the video, and then come back, and we will show you kind of the solutions to what you should have. All right, so coming back to the first one that you had to try on your own, this is what you should have. A value 2, h value 0, k value -4. The vertex, optimal value, axis of symmetry, direction of opening should all have been fairly straightforward. The step pattern will have been different because now our a value is something other than 1. So when we plug it into that general form, 1 times a, or 1 times our 2 in this case, is 2. 3 times a, or 3 times 2 is 6. 5 times 2 is 10. So that's where we get this new step pattern of 2, 6, 10. Number of x-intercepts, again, we plot the vertex. We can see that it opens up. So when we graph it, we should cross the x-axis twice. So there are 2 x-intercepts. Transformations, again, that should be fairly straightforward. We can say now that we have a vertical stretch by a factor of 2 because our a value is 2. Looking at our graph, again, we graphed it the same way. Plot the vertex. We used our step pattern. We can see here in red. It's a little bit different because we're not going up by 1 and then up by 3. We're going up by 2 and then up by 6. So we can see that our graph has this stretched look. It's now looking a little bit skinnier and a little bit taller in comparison to our other ones. We can't really graph that third step because that's going to take us off our grid, which is fine because we can draw the arrows to represent that it goes on forever, or it's continuous. But that's the third example. The next one you were to try on your own, we have here, again, A, H, and K hopefully were fairly straightforward. Vertex, optimal value, axis of symmetry, direction of opening. Step pattern in this case, if you got the last one correct, then this one should not have been a problem. The A value was 2, so again, following that 1A, 3A, 5A general form, we get 2, 6, and 10. Number of x-intercepts in this case, if you plot the 0 at 6 and 1, and notice that it opens up, it's not going to cross the x-axis, so we're going to have no x-intercepts. Transformations, we had a vertical stretch by a factor of 2, same as the last one, a shift right of 6, and shift up of 1. Plotting the graph, same idea. Plot the vertex at 6 and 1, coming from the h and k value. Use the step pattern, 2, 6, and then 10 to graph it. So we start at the vertex, move to the right 1, up 2. Move to the right 1, up 6. We would technically move to the right 1 again and then up 10, but it doesn't fit on a graph or a grid, so this is as much as we can draw. Repeat that pattern on the other side, or use the idea of symmetry to find the other half of the graph, and there we have our quadratic. I'm going to move into 2 more examples. We're going to pause the video again to give you a chance to work on these on your own. Again, if you have the lesson, otherwise you can pause it and try to copy it down, or you can kind of wait through. But again, I recommend trying it on your own, and we'll pop in a little bit to show you the solutions. So the next example that you should have tried on your own, this is the solution. So here we have an a value of 0.5, h value of -3. Again, remember it's the opposite of what we see in the bracket, and a k value of -5. Vertex, optimal value, axis symmetry, direction of opening, hopefully we're okay. Step pattern was a little different because we had a decimal in front, but we still followed that same general pattern, 1a, 3a, 5a. So 1 times 0.5 is 0.5. 3 times 0.5 is 1.5. And 5 times 0.5 is 2.5. So here that's where we get this step pattern. For the number of x-intercepts, if we plotted our vertex -3, -5, and then saw that the direction of opening was up, that tells us that we're going to cross the x-axis in 2 spots. So we'll have 2 x-intercepts. Our transformations, because our a value is a decimal between 0 and 1, we have a vertical compression now by a factor of 0.5, which we can see in our graph because it tends to look wider and shorter than what it normally is. We shifted left 3, and we shifted down 5 as well. So those are the 3 transformations that we have. To graph it, this one may have been a little tricky because our step pattern was slightly smaller, but the same idea applies. We plot our vertex at -3, -5, then we move over 1 up the first step, or 0.5. There's a point. Move over 1 from that point again, up 1.5. There's our next point. Move over 1 again, up the next step, or 2.5. There's another point. We can repeat that same pattern on the left side, or we can just use the idea of symmetry to fill in the other side. And there is our quadratic. And finally, the last example, y equals -2x squared minus 4. A is -2. H was 0 because there's no bracket with the x. So there's nothing being subtracted or added in a bracket with x, which means the only value for h that we could have, where we don't have to show it, is 0. And then our k value, we can see it's the number that's after the squared, and it's -4. So again, vertex, optimal value, forgot to add in that it was a maximum because it's opening down. Our axis of symmetry should all be fine. Step pattern, we've dealt with an a value of 2 because it's negative. That just means our numbers or our steps are negative because we're opening down. Number of x-intercepts, again, we plotted our vertex at 0, -4, saw that it was below the x-axis, and because it opens down, we're not going to cross the x-axis at all, so we're going to have no x-intercepts. Transformations, here we flipped because we're opening down. We have a vertical stretch by a factor of 2 because our a value is greater than 1. And we've shifted down 4 because of our k value. To graph it, we graphed our vertex at 0, -4, and we applied our step pattern. Move 1 to the left or right, and we go down the first step. In this case, we're going down because of the negative. So we go down 2. There's a point. If we wanted to continue this, we'd take 1 step to the right again and go down 6. Fortunately, it doesn't fit on the graph, so we can't really show that. We can show on the left side, though, the one other point, the symmetry that we would have. We can't show the second point because, again, it would be off our graph. But we can roughly show what it would look like. So this is our graph of y equals -2x squared minus 4. So the main thing from this note is just making sure that you can recognize the a, or identify the a, h, and k value from vertex form, identify or recognize all these key properties of the quadratic using that vertex form, and then you're able to graph it using the vertex and the step pattern. If you need practice with the transformations, again, look in the previous lesson, or there is a worksheet for this lesson as well to practice, again, this idea of finding all this information.